Look at that, 1 out of 10. 1 out of 10. There you go. There we go now. When you come in, just answer the start. Before you start the starter activity, you're logged on. You'll find your 3 pause tasks. You won't be able to start them. They are paused, but if you're all logged on ready, that will be amazing. You'll see the keywords on the starter. Now, there's no right or wrong with this, with how you use these keywords. Some of you might be able to use them all and feel as if you are a genius and can use them all in the best scientific context ever. Some of you might feel that you can just use 1 or 2 and perhaps describe them in a slightly different way. That's all fine. There's no right or wrong. You'll see the 3. So on this task here, just have a go on the back on the starter. Try and use those words in whatever context you can. Maybe some of those words you've come across and you kind of are familiar with them. Maybe you can use them to properly describe an atom or an ion or an isotope. Just use them in the context that you can. So my name is Mr. Hayes, and hopefully we'll get something out of today. I believe that we've looked at atomic structure in the past, yeah? We've looked a little bit at isotopes. I'll introduce some fresh learning objectives for you in a minute, but first of all, I want to show you this. It's only a very, very short clip, but I want to see what your I don't want to tell you what's going on. I want to hear from you what you think is going on here, based on the science that you already know. The video starts off with this young man here holding an ice cube in his hand, and the ice cube is floating. That ice cube is made out of water, right? Obviously. And in a second, we're going to see him pick up another ice cube. This ice cube, I promise you, you know, is also made out of pure water. What's going on here? So, why is that? Yes, your man. Right, in this second ice cube, for some reason, the water must be more dense. That's why it's sinking. But it's water. It's just water. It's made of 2 hydrogen atoms and an oxygen atom, just like the other ice cube. So what's going on? Why might that be?
The second one has more isotopes and hydrogen oxygen.
More isotopes. Now, I love the fact you pulled out that scientific word there. I love that. Can anyone help build on that? More isotopes. Whoa. How can we improve on that? What does that perhaps mean? More isotopes. It's really good. See if I can grab some else, but I will come back to you. Remember what's your name?
Irfan.
Go on, Irfan.
Is it because some of the elements inside the ice cube have more neutrons than their normal average element? Like, for example, hydrogen has 1 proton, I think.
And that is an excellent answer that would link in to what Irfan said over here. Faris has said over here about isotopes, of course. Now, I feel that there's a lot of information in this room just from what you've said alone about that, but we can tweak and improve perhaps on the language we've been using there. Now, you will find out exactly why this sinks and the other one floats, and we'll also find out why this particular type of water that has been used to make this ice cube isn't a very reactive type of water when we mix it with group 1 metals. Okay, you'll find that, but you're going to teach me. Somewhere in this lesson, that information is out there. You're going to hunt it, and I promise that I just might, or might not, give whoever tells me first £1 million. Now, I might not. I'm not signing that away, but I might do. Go on, young man.
Is it because the water in the second one has more electrons, so it's less reactive?
I love the way you're thinking. I love the way, but we need to investigate. We need to investigate. So, we're going to just recall our understanding of subatomic particles, the structure of an atom, where we find, you've used some great words already, protons, neutrons, brilliant. We're just going to recall our understanding of that. We're then going to really nail down, Ferris, you used that great term isotope. We're really going to nail down what that means. We're actually going to find out what some isotopes actually are used for in the real world, including that one that was used to make that ice cube. Hopefully, if we've got time, we're going to end up with something a little bit more complex, looking at why, when we have isotopes of an element, perhaps, why that can make it difficult sometimes to say how much an element should weigh or what the mass of an element should be. I have on the screen here an image of an atom, and all I want you to do when I send this question out to you is to give me 3 facts about the atom. Now, those facts can be as complex or as simple as you like or as you are able. Everybody can access this. You can go really deep and use the scientific terminology that was on the starter that you've just used, or you can be a little bit more general in what you say, but everybody can access this question in one way or another. you should now all have a little text box where you can describe the structure of the atom on the screen using those words, hopefully that I gave you in the start. Use as many of those as you can. And I'm going to give you maybe about 60 seconds to do it. And I'm going to bring up some of your answers, and we're going to have a look at how you're using that terminology that was on the starter, how we understand that terminology. Go on. Everybody can access this in some way, even if all you can say is, it's an atom with some things in it. If that's all your knowledge is, you can still say that. And that's going to be really useful for me, as somebody who's only just met you. Would it help if I dim the lights a little bit so you can see the... Yeah. So if I dim those lights a little bit just for now, that might come up on the board a little bit more clearly for you. And we need about 90 seconds just to write what you can about what you see on that board. Remember, there's no right, there's no wrong. I'm not looking for perfect. Looks looking excellent. Superb stuff. How are you getting on, young man? Very good. So I can see some of you still typing. I don't want to bring this up too soon. 47.6 seconds, that's how long I'm going to give you. 47.6 seconds. Can you keep time? Some really good work going on over here. How are we getting on? You've got something to say? Yeah, okay, excellent. Everybody's got something to say. Right. In about 10 seconds, I'm going to call this to a stop. Right, let's see how we got on. Who found that difficult? Let's just have a show of hands. Stop. Just a couple of gaps here, or might these be from students who aren't in the lesson? So, what did we find out? We found out it's an atom with protons, neutrons and electrons. And it shows the electronic structure. I'm not going to ask you to embarrass yourself and put your hand up and say that was mine, although that's a great answer. And it does do that. It does do that. I think there's a lot of positives there. Who can add something to that? What was just your mind?
You could identify that the protons and neutrons are inside the nucleus of the atom.
Brilliant. The location. Protons and neutrons inside the nucleus. As such, protons and neutrons sometimes get given a name that kind of indicates that we find them in the nucleus. Your name, young man? Lewis, go on. Nucleons. Brilliant. Well done. Yeah, really, really impressed. So that would be somewhat brilliant we could add to that answer, the location of the protons and neutrons. Right found inside the nucleus. Excellent. Let's see this next answer here. The model of the atom, I like that, the model of the atom, okay, shows that there are electrons in the outer shell. And it's important to point out, actually, that when we look at atoms in that way, it is just a model. It has got strength. It has got limitations. There are electrons in the outer shells. In the outer shells. I really almost love that. Really almost love that. How can we tweak that? The outer shells. Go on. Yeah, we have electron shells, and the outside one, right, the valence shell, the outer shell, there's one outer shell. They're not all outer shells, there's shells, and then we have the one on the outside. That's really good, though. Another thing is that the protons and neutrons are inside the nucleus. Fantastic. The nucleons. These two things create the atomic mass of the RO. That's amazing. Atomic mass, the sum of the protons and neutrons. I like that. And the electrons are equal to the amount of protons inside the atom. Let's just dwell on that for a second. Let's dwell on that. Why do we need, do you think, the number of protons to be equal to the number of electrons in an atom?
To make the charge of the atom, I can't really explain it, but like no positive charge or no less charge.
We're equally charged, because what charge, anyone help me out, what charge do protons have? What charge do protons have? Yes?
+1.
Excellent. A relative charge of +1. Yes, relative charge +1. What charge do electrons have?
-1.
That is absolutely smashing it. A negative charge or a relative charge of -1. A relative charge of -1. Okay, so it's time for you to do a little bit of work and do some learning for me before we delve into a full LBQ question set. Now, there are 1, 2, 3, 4, 5, 6, 7. There are some people in this room, and I'm going to place you in a group. So you're group 1. Young lady, the two boys behind, you're group 2. Ferris and and okay, you're going to be a group, you're going to be a group, and then we've got a group here up to Harry, and then we'll have 2 groups of 2, rather than a group of 4. Now, what you'll find on the desk here, you're going to find a mind map that needs populating, and it needs populating with information about isotopes, what isotopes are, what different types of isotopes could we possibly be aware of, what are the jobs of these different types of isotopes. And what we're going to do through this lesson, through the information I give you and through the feedback you get from the LBQ task, is you are going to teach me what isotopes are. You are going to teach me what the uses of these isotopes are. You are going to have 7 minutes. One of you in your group is going to come up and collect one of these pieces of paper, and then they're going to go and sit down. Another person in the group is going to get up. We're going to move around, right? And you'll notice that around the room here, we have information about various different isotopes. And I know some of us might be feeling, I'm still not sure what an isotope is yet. I'm going to be getting there, okay? But you're going to see lots of information around the room about a different isotope. And I want one person, just one person from the group, to come up. And I think that what we're best doing here, actually looking at the layout of the room, is we're best taking this back to our seat. And as a group, we're going to have a look at the information on there, and we're going to add it to our mind map before the next person brings it back and collects another one. Now, Year 9, you're intelligent people, aren't you? And I know what a shortcut to this would be. A shortcut to this would be taking all 6 and sitting down, right? That's not what we're doing, because we haven't got enough space for that. And it's not the task. You'd be getting up and moving around. Yeah, a bit of cross-curricular link with PE. Let's get some steps in. So we're going to take one at a time. We're going to bring it back. We're going to look at it, and we're all going to attach it to our mind map. And you're going to have 7 minutes only for that. Everybody, let me just clarify, everybody in the room is going to need one of these. So whoever comes up and collects one of these needs one for each person in the group. You've got 7 minutes. Impress me in 7 minutes with how much information you've collected. Yes, Ruban?
Do we have to all write the same thing?
We are building, we are going to be adding to this when we do the question set later on. There's more information in the question set that we're going to add to this, and everybody is going to need their own individual mind map for your notes. Yeah? And as the lesson goes on, we'll keep adding to this. Go! 7 minutes. Right, remember time is of the essence here, guys. We've got 7 minutes of 6 isotopes. What is the key important point? And we're adding that to our mind map. We're extracting information. We're not copying information, we're extracting information. I would imagine in the next 15 seconds somebody will be getting up and swapping those sheets. Because we're extracting some key information. There we go. It's not Adam. It's
Carbon 14
I know, I keep calling
is an
Adam.
isotope of
Go on, what's your
carbon.
name, sorry?
She just wrote the first sentence.
Sorry, okay, let's be a bit more lively, Year 9. Come on. As fast. Some of us are already on our second, which is great. Some of us are just lagging a little bit behind on the first. We're extracting the information only. We're not copying.
No, I haven't even done it to be honest.
Look at the sheet. Read the paragraph. Think to yourself, what is the key point on here? And the key point is what you're extracting. It's not a copying task, it's an extracting information task. These guys are already on the second, almost on the third, which is excellent. Well done, lads. Also over here, these guys are on the third. Fantastic.
Wait.
Brilliant. You've done it first. You've done it. Now,
I'll do that one.
I'm going to say we've got about 3.5 minutes. We're not all going to get all the information, but that is not a problem. It's not a problem. We'll get what you can. We've got 3.5 minutes. Ultimately, what can you teach me from this? Okay, that's excellent. This group here are absolutely storming it. I can see what they're doing. They're on the fourth one here. They've read it, they've extracted the key information, and they've written it down. That's awesome going. this group's smashing it. How many are we on here? Look at that. Awesome. Awesome. Extracting the key information. 2.5 minutes. One and a half minutes, and now at this point you'll be thinking, oh, I've not got all the information I need yet. Don't panic. 1.5 minutes though, that is strict. I promise you I'm not just counting down in my head, I've got a stop clock somewhere. This group over here nearly finished. We're in the last 60 seconds. You're smashing. 35 seconds. I know some of you are thinking we're not going to get it all. You're not, but don't worry about it. And now to put it. Pens on the desk, please. High to spray, everybody. Totally blown away with how well you did that. I was expecting you to get far less information actually than you did. You've done an outstanding job. We're going to have a quick chat in a minute about what you found, and we're going to add to what we've learned through the use of an LBQ question set. But why don't you just teach me something, because I don't know anything about isotopes. That's why I've not mentioned them yet. I don't know anything about it. Who can tell me maybe the use of an isotope? Who can tell me something that you've learned today? Don't be shy. Go on, you man.
For the use of isotopes, we found out that an isotope of hydrogen can be used to create what's called heavy water, which I think you used for your ice cube.
Oh, amazing. We're going to find out more about that. Yes, an isotope. Did anyone pick up what the mass number of isotope hydrogen was? Young man, go on. 2. Brilliant. So what does that mean if it's got a mass number of 2 and an atomic number of 1? What does that mean? Fergus. It's got an extra. How many protons has it got if it's got an atomic number of 1? Good lad. And an extra neutron. So how many neutrons? It's got an atomic number of 1 and a mass number of 2. How many neutrons overall? 1 neutron. Fantastic. Now, I know I feel like I'm speeding through this. Believe me, this will all come together. But for now, I just want to tie together some of the language that we've been using before I set you off on a question set to really tie together the information that you've found so far and the things I've said. If I wanted to know what element this atom belonged to, how could I find out? Lads, you are doing superb, and I will come to you. I'll just see if I can fire this somewhere else just to get, and you're doing amazing. I'm just going to fire this to you, man. If I wanted to figure out what atom, what element that atom belonged to, how can I do it? Okay, I could find out how many electrons it has. And it has 7 electrons. 1, 2, 3, 4, 5, 6. Oh, it does not have 7 electrons, does it? It's got 10 electrons, isn't it? 10 electrons. Yeah. How many protons should it have in its nucleus? Go on. 10. So we've got something wrong here. Remember before I asked you about the protons and the electrons, and somebody gave me the answer earlier on. Right? So why is that not quite enough? What kind of, how would I describe this? I wouldn't describe it as an atom. What would I describe it as? It's got 2 more electrons than it has. It's got 1, 2, 3, 4, 5, 6, 7 protons. It's got 10 electrons, so it's got 3 more electrons. How would I describe that?
Is it an ion?
Yeah, it's not really a, it's not even an ion. It's got nothing to do with lessons. How am I going to correct that atom? What am I going to do to that atom to make that ion to make it an atom? What do I need to remove to make that work? What do I need to remove? So let's do that. Let's remove 3 electrons. Fantastic. I'm happy with that now. But how do I know what element it belongs to?
Your protons, however many protons there are.
Brilliant.
That's what every atom is identified by.
Some things are planned. You see, if I want to count the electrons around an atom, we're all used, as we are looking at elements on a periodic table, to look at the atomic number and think, that's the number of electrons and it's the number of protons. But the number of electrons inside an atom can change. We can gain them, we can lose them to become ions. So we don't describe an element as being defined by the number of electrons it has, because that can change. We define it, as you've said, as being defined by the number of protons it's got. So how many protons has this got? 7. Anyone know what element? Lithium has a mass number of 7, but not an atomic number of 7.
It's a nitrogen.
You're a legend. Now, if I look at nitrogen on the periodic table here, How many neutrons should an atom of nitrogen have? First,
7.
it should have 7, shouldn't it? Right? We subtract, we look at the difference between the atomic number and the mass number. We should have 7 neutrons here. But let's have a look at our atom of nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Is that a mistake?
No.
Why? Why is that not a mistake? It's the word, the big word for the lesson. Ferris again. It's an isotope. Right? Every single element on the periodic table has different versions. Listen, it works like this. At some point in time in the past, a nucleus come together over here, right? Containing 7 protons, and it just happened to pull in, let's say, 7 neutrons. But because it had 7 protons, remember we define an element by the number of protons, not electrons. Because it had 7 protons, we just call it nitrogen. But it happened to pull in 7 neutrons. While over here, in a completely different part of space, we have, again, 7 protons coming together. So what element must it be that's got 7 protons? What does it have to be that's got 7 protons?
Nitrogen.
Awesome. Right, just like that one over there. 7 But over here, it pulled in 8 neutrons into the nucleus. We don't care. Not at GCSE. We don't care about the neutrons. They're not important. Alright? But it's still nitrogen. And that's really what isotopes are. They're just different versions of the same element. And the isotope, something I often find people struggling with is not understanding that they are isotopes of each other. Alright? It's like when 2 people are brothers and they're like, well, which one's the brother? Well, I'm the real one. He's the brother. Well, no, I'm the real one. He's the brother. They're brothers of each other, aren't they? And that's what it is with isotopes. All these elements we see on the periodic table, yes, they're isotopes. They have other elements that are isotopes, and the way they differ is simply by the number of neutrons in the nucleus. Now, it's time for me to shut up and get you on your LBQ question set. I'm going to unpause task 2. That's going to bring together everything that we've talked about so far today. So can you do that, please? Now, what you'll find when you're looking at task 2, I want you to turn your mind maps over as well. When you are doing task 2, in the feedback, the correct feedback and the incorrect feedback, you will find fresh information to add to your mind maps on isotopes. Yeah? This is learning by questions, not just doing questions. So when you have done a question, the feedback will give you something new to add to that mind map so you can tell me at the end when we bring it together. And I'll be coming around helping people as and when I can. And I want to see people showing me what they are learning from the questions by whacking it onto that mind map as we go along. All right? Off you go. So while the students are answering the questions, I can see on the live data matrix here exactly which students are getting which questions right, exactly which students are getting which questions wrong in real time to the very second, really. I can see how many attempts they've had at each question, and I can see who's not answered any questions for quite some time. And that just all allows me to be where I need to be in the classroom, when I need to be there to help the correct students in real time. It's really powerful. So remember, yes, young lady. You know, I've got to say, you've been absolutely outstanding today. Now remember, there will be questions here, especially when you get to the isotope questions and the uses of isotopes. There will be questions here that will allow you to add extra information to your mind maps via the use of that feedback. You've collected an awful lot of useful information. Not everybody managed to get everything, but you've collected an awful lot. And it doesn't matter if you didn't manage to get everything, because you're going to find it all in this question set, plus more. Ferris, young man, can I just say, you've been outstanding.
Mr. D. Oh my god. No, true. I didn't ask him. How? Oh, you should have been happy.
So question 8 was one that is in
Which ones have you tried so far?
this,
This, no. So the first and second one?
About these three before we even start. Why are all these three considered to be atoms of carbon? Why are they all carbon atoms?
Because they all have the same number of neutrons, electrons. Sorry.
Right, found inside the nucleus. If we look at the date of the image at the bottom, found inside the nucleus, got positive charge. What have they really got all the same number of? And what is that? Electrons, neutrons, protons?
Fossils. Dating fossils.
which of these three atoms has the most
Yeah, right. Same with
might have? How would you figure out how many?
use of? What did I say? Bloody hell, no, the gamma one. Yeah, I finished that one now.
Okay. So the fact that they all have the same number of protons, T1 and 2 still facing. Now, you've done a brilliant job searching for a lot of information this lesson. You've found out about various isotopes. Hopefully we've pinned down some of the language about isotopes through what we've discussed, the question sets. You've done a great job. Now it's time to put it together a little bit. I'm going to explain a task that I want you to carry out. Hopefully it'll be a slightly entertaining task. And while you're carrying that task out, if I can remember where the computer is, I'm going to be coming around and having a little bit of a chat with each of you based on the data that we've just taken from that question set. I'm going to come around and just clear up any misconceptions that we might have. I can see that there's some of you that I didn't manage to get around to who maybe took 3 or 4 goes on a particular question or got a question wrong. And I'm going to come and just have little private chats with you while you're all putting into practice what we did over here. So, I'll get rid of my electron scribbles. I created, before I came, a model of an atom. And I think this model of an atom is meh. I think it's alright. I think it could be better. Well, that really hurts my feelings. I did try as hard as I could. There's got to be something good about it. Yes, go on, you man.
You've kept the, what I assume is the protons and neutrons inside the nucleus.
Yeah, I should have labelled it, shouldn't I? And maybe I could have put some information about the protons and neutrons, could have written some information about it, like the relative charge, the relative mass. I'm not too happy with my electron shells now I'm looking. Perhaps they could be improved. Go on, how would you improve them?
You need to start off with 2 electrons in the first shell, and then it can go up to 8 after, so you would just put 1 in the next shell after that one.
That is fantastic. That's just clamping down for me over there with you a second. It's just a little bit distracted. That is brilliant. I could really improve that. That's excellent. I could maybe label the type of element it is, or the type of isotope it is, perhaps. And that's what you're going to do from now. You're going to show me that you can build a far better model than I can. And if you look at the back of the room, you'll see that I have brought lots and lots and lots. Oh, yes, Play-Doh. Lots and lots and lots of little pots of Play-Doh, all different colours. Now, I don't need to come and take all the pots. I know we can share, but I'm going to place a pile of paper on the front in a minute, just like the one that I've got over there. And using your pens and using the Play-Doh, you're going to create a much, much better atomic model than me with all the detail that has been discussed today, with all the detail that you've extracted from that question set. But not only are you going to make just any old atom, you're going to make an isotope that you've learned about in today's lesson. And you're going to write next to your little model what element it's an isotope of, why it's an isotope, and what the use of that isotope might possibly be. All that information is what you found from yourself from the question set today. While you're doing that, I'm going to be coming around the room using that data matrix to try and speak to some of you about some of the questions that maybe we slipped up on or slowed down a little bit on during that last task. Blank paper! You're more than welcome.
Oh my god, just get
Now, all subatomic particles in real terms have a small mass. Like an electron is like 9.1 times 10 to the minus 31 kilograms. Tiny, tiny things. Which is why we don't talk about protons, neutrons and electrons in terms of having a mass in kilograms. We talk about them in terms of relative mass. And because protons and neutrons are roughly the same size, we say they have a relative mass of 1. And because electrons are tiny, we say they have a relative mass of 0. So they have a very small real world mass, but they have a relative mass of 1. And that's where you've gone wrong.
Look how big that is.
Get that.
But what she made it. I'm doing it.
Okay, he's just I think I'm just. Oh, yeah. Oh, it's too small, like, we're not gonna fit
Why are you making it so big?
We'll end in 20 seconds.
21, 20, 19.
I know you said you're making 5. Why are you making 6? I don't know.
Let's just have I'm just going through the matrix a little bit, and see number 12, you finally got it right, but it did take 5 attempts, and it was just one of the questions clearing up the uses of different isotopes. So obviously we know you've got it right in the end, but let's just have a quick chat about that. The isotopes that we were looking at were, for example, deuterium, the hydrogen isotope. Do we know what a use of deuterium might be? Is that there? Okay. Remember the video I showed you at the start of the lesson with the ice cubes? And one of the ice cubes, how would you describe something that sinks as opposed to being light?
It's quite heavy, it's got a high density.
Yes, actually the high density is a much better scientific term, okay? But water that has that high density is often made from called deuterium. It's the isotope of hydrogen. It has an extra neutron. What about uranium? What do we use uranium for?
For radiation.
Okay, so uranium is a radioactive isotope for sure. We want it to have an unstable nucleus, so its nucleus can split apart, but we use it in a very specific place.
Blood clots.
Now you're thinking, you've got the uses, haven't you? You've got the uses, but perhaps not matching them up. What if I said to you a nuclear reactor? Which one of those would you use in a nuclear reactor? I'm guessing this is some really good stuff. But I just noticed in here, one of the core aspects of today's lesson is about being able to identify the isotopes. You did get it right in the end, you had a couple of goes. So, okay, now they've both got the same number of electrons, which is right. Now remember before, when we had the discussion on the board about atoms being able to gain or lose electrons, and that's not really the best definition of what an element is in terms of the number of electrons it's got, because it's an ion, it could have more or less. We talked about protons, didn't we?
Oh, I wish this was the full year, you know.
So, yes, you're right, they've got the same number of electrons, but really what we should be saying is they've got the same number of protons. Yeah, because you could gain or lose and be an ion. Brilliant, well done. Can you just please push your Play-Doh away from your hands just for a second? That'd be amazing. Right. Look at that, thanks. Unite, first of all, you've been absolutely outstanding today. Really, really outstanding. Down to a T. Everybody I've spoken to has been absolutely amazing. Really done yourselves an absolute credit, and I'm really grateful. So thank you so much for the time. But let's wrap this up. We've talked about why perhaps
atoms of the same element can have different number of electrons when we're thinking about ions. We've talked about how they can have different number of neutrons. Let's tie it all together with this. I'm going to ping this question out to you in a second, just like I did at the starter. And when I do, I want you to describe to me two things. The first thing I want you to describe is what the structure of this atom would look like. So what parts of this atom will be in what places, and how many of those subatomic particles will be in each place inside an atom. That's question number one, describe it. Question number two is to tell me what a different isotope of this atom might look like. What might a different isotope of this element look like? And of course you've got multiple options with that. So I'll send this out to you. This is going to be on task 3, which is going out to you now. That atom would look like in terms of where the protons, how many are there, how many neutrons are there, how many, and you're going to describe what an isotope of that atom might look like. And that's the key. You know, can we suggest what the makeup of an isotope of that atom? Using the atomic number, using the mass number, you can describe what that atom might look like. So how many protons might. How would it be different to what you see on the screen there? Let's think about that. Just tell me vocally a little bit before you start. How would an isotope look a little bit different? What would be the same between this atom here and another isotope of magnesium? What would be the same? The number of protons. What would be different? So would this number, which is the number of protons, would that change or be the same? And this one, which is the number of nucleons. Yeah. You know, I can have something else stand here. So here's what we've got back, and again I won't be asking anybody to identify themselves unless it's a particularly brilliant answer and you want to jump up and give us a dance. I can see that magnesium has 12 protons. I would agree with that, which are located inside the nucleus. I would agree with that because they are a nucleon. This atom also has 12 neutrons. I would agree with that. We know this because to find out the number of neutrons you need to do the atomic mass, or the atomic mass number minus the proton or atomic number. Brilliant. Absolutely fantastic. And to go one further and give me the electronic structure of 282. That is actually genuine. You don't have to identify yourself, but if you would like to claim ownership to that answer, right, round of applause for the man. Now, last question then it's time to go. How would an isotope How would an isotope of this look different?
Since an isotope is an atom that has more or less neutrons, you could either have 25 or 23 neutrons, or as your...
Very close. We could have a mass number of 25 or 23, but does this actually have 24 neutrons? No. So we'd have a different mass number.
Yeah.
That is amazing.
For example, if you had 25 as your mass number, and then find out neutrons, as I've said there, you take away the proton number, which would be 12. Then you had 13 neutrons, which would be an isotope.
You're a legend. Now, so you nine to complete this journey at home, to see what we can retain at home, to see if there's any other gaps that we need to fill next lesson. We're just going to finish this off with a bit of independent study. The question set I want you to answer is all about atoms and isotopes, hence the amazing name, atoms and isotopes. I will set that here for you, and let me think. You've been so good today. When do I want this back? I think I want this back on Friday, please, and I'm going to give you till 8 o'clock at night, because that's when I put the kids to bed and I managed to get a bit of marking done. Not that I need to mark, but they'll be cute, obviously. It'll be done for me. Little message. Thank you in there. And I think we are good to go. You nine, absolutely fantastic. Thank you so much.